So now that you are already familiar with several classes of organic compounds such as hydrocarbons, alkenes and alkynes, halides and alcohols, ethers, aldehydes, ketones and organic acids, it's time for us to talk about how some of these compounds are formed, what kind of chemical reactions lead to formation of these compounds, and what kind of chemical reactions some of these compounds can undergo. Today, I would like you to get familiar with 7 organic reactions: substitution, addition, polymerization, combustion reaction, fermentation, esterification reaction, and saponification reaction. You will notice as we describe them and learn about them that their names are very, very descriptive to what they do and what is happening in them. Let's start with the reaction of substitution. It involves replacement or substitution of one or more of the hydrogen atoms in saturated hydrocarbon. It is replaced by an atom or a group of atoms, but the important point that I want you to notice that substitution reaction is happening to the saturated hydrocarbons. And here is an example of one of these substitution reaction. Here is methane, saturated hydrocarbon, and here is a molecule of chlorine. Chlorine is a diatomic element. This is why you see 2 chlorine atoms connected here. In this chemical reaction, light helps chlorine to break the bond between 2 atoms, and one of these atoms, being highly reactive, goes and knocks out of its place hydrogen and takes its place. It binds to the methane. Now this new product is chloromethane. Well, the hydrogen that was now knocked out of its place now has need to bind to something, and the remaining chlorine that wasn't participating in this reaction up until now is ready to bind too. So they together form this compound here, HCl. Let's see how similar reaction happening between this ethane, once again saturated hydrocarbon, and this molecule of bromine. Bromine gets separated into atoms of bromine. One of those atoms goes around and knocks out the hydrogen out of its place and replaces it, substitutes hydrogen in the molecule. So over here, as a product of this reaction, we now have bromoethane. And the remaining molecule, the remaining atom of bromine that was not part of substitution reaction so far, now will bind with the hydrogen that was knocked out of its place, forming this HBr compound. Now let's talk about addition reactions. Addition reactions involve adding one or more atoms to a double or triple bond. So this time around we will be talking about reactions that are happening to unsaturated hydrocarbons. In addition reaction, the double or triple bond will be broken to accommodate for the addition of the atoms. Let's look at this reaction of ethene and hydrogen. When ethene meets hydrogen, it breaks this bond over here and attaches the hydrogen. So both hydrogens are getting attached to the carbons. You can see that on the left we have two reactants and only one product on the right, because both atoms of the hydrogen molecule were added to the ethene molecule. Now, as a result of this reaction, ethane has been produced. Here is another example of addition reaction. A bromine, molecule of bromine, Br2, is getting added to ethene. Once again, not ethane. Addition reaction happening to unsaturated hydrocarbons. So in this case, we're talking about ethene. Ethene has a double bond, and one of those double bonds will be broken in the process of this reaction. Ethene will attach bromine to carbons, and you can see that the one bromine goes to one carbon, another bromine goes to another carbon, and we see both of them being part of the molecule of 1,2-dibromoethane on the right. Once again, I wanted to remind you that addition reaction happening only to unsaturated hydrocarbons, alkenes or alkynes, those that have double or triple bond. Interesting part about addition for addition reaction that sometimes you can end up with having different isomers as a product of the same reaction. Look at this propene. Propene is running a reaction of addition with HBr. And since we're not in control where hydrogen and bromine are going, they attach themselves on carbons that used to be adjacent by the double bond. So we have relatively equal chances of having one bromopropane as a product of this reaction or two bromopropane as a product of this reaction. Here's the last example of addition reactions. Okay, over here we have ethene that is adding water. And adding of water in the formation of alcohols is easier to see as an addition reaction if you view molecules of water as H or H compound. So once again, one of the double bonds here in ethene is broken and one of the carbons attaches hydrogen and another carbon accepts hydroxide group and attaches it to the molecule. So as a result, we have ethanol being formed. Okay, here is a reaction of polymerization. It is a linking of small molecules, we call them monomers, together to make large long chains of molecules, we call those polymers. You are quite familiar with natural polymers such as protein, starch, cellulose, but you also probably use considerable amount of artificial polymers created by man, such as nylon and rayon or polyethylene and other synthetic polymers. Okay, so how it's happening? Well, here is ethene, small molecule double bonded between two carbons. But if I have many of them, numerous molecules of ethene, and if they break one of those double bonds, they will have an electron extended, be ready to bind to another molecule that is also ready prepared to bind. So over here it looks like this. This single one of those double bonds is broken down. And since each bond represents two electrons, it means that after bond is broken, there is two electrons on this end of the molecule and this end of the molecule extended as an arm ready to be binding to another molecule that is also ready to share an electron. And as a result, we have a long chain of these molecules created, binded to each other. Here is the same idea represented in a slightly different way. Here we have three molecules of ethene. In each of them, one of the double bond will be broken, and they will extend that broken bond as electrons towards each other to bind, to share those electrons, and thus create this long chain of molecules. We have total of 6 carbons in initial molecules of ethene because we have 3 ethenes. And look, we still have all of these carbons now in a newly formed chain over here. Okay, combustion reaction. Almost all organic compounds will burn. They will react with oxygen and they combust and produce considerable amount of heat. Hydrocarbons burn with the producing carbon dioxide and water. This is example of complete combustion when there is plenty of oxygen, and in this case the products of the combustion of hydrocarbons would always be carbon dioxide and water. This is the most classical example of it. So we have hydrocarbon reacting with oxygen, producing carbon dioxide and water. And this is the sign that you are looking at the combustion reaction. And here is a much rarer example of combustion reaction. It's so-called incomplete combustion reaction. It is happening when supply of oxygen is limited. So you can see here that the products of this reaction, carbon monoxide and water. So once again, we have hydrocarbon on the left reacting with oxygen, but since oxygen is scarce, it's not carbon dioxide that is formed, it's carbon monoxide. And actually that's quite dangerous because carbon monoxide our body mistakes for oxygen and starts to deliver it instead of oxygen to the tissues of our body. So this is why carbon monoxide is toxic and very dangerous. It can kill. Okay, fermentation reaction. This is reaction that is producing ethanol, the drinkable alcohol. The enzymes from yeast catalyze the reaction of sugar breaking down into ethanol and carbon dioxide. So it is as simple as this. The glucose on the left, aqueous solution, and ethanol, the alcohol, and carbon dioxide on the right. That's it. And now reaction of esterification. Esterification, formation of esters, is a reaction between an alcohol and organic acid. Here is organic acid, here is the functional group of organic acid, and here is hydroxyl group that we'll find in alcohols. Okay, so when alcohol meets organic acid, they detach this hydrogen and this hydroxyl group, and that goes to form water. And the remaining parts of the molecules, they combine together to form a new compound called ester. Ester have this interesting connection of one part of the molecule to another through the carbon that is double bonded to oxygen and through the oxygen to the rest of the molecule over here. So this is how functional group of ester looks like. Here's another example of esterification reaction. Here's my alcohol, methanol. How do I know it's alcohol? Because of the hydroxyl group that is sitting right here. And here is my ethanoic acid. I know it's ethanoic acid because I see carboxyl group right here, and I see 2 carbons. So ethanoic acid. Acid meets alcohol. What do they form? They form ester and water. So hydrogen from the alcohol, hydroxyl group from the ethanoic acid get together to form that molecule of water that we see on the other end of the reaction. The remaining parts of the molecules glue together, connect together to form methyl ethanoate. This is how we name esters. We take the part that used to be alcohol and call it methyl, and then we'll look at the ethanoic acid. It changes ending, so it's methyl ethanoate and water. Also, I can add that you are very unlikely will be asked to write the reaction of esterification, but you should know that alcohol and acid form ester and water. The last of organic reaction that we're going to talk about is saponification reaction. You should know about it, you should know what are the reactants and products, but you are not going to be asked to write this reaction. You should be able to recognize it though. Okay, saponification reaction is a reaction of formation of a soap. Well, ester reacts with inorganic base. Here is my ester. How I know that it's ester? Because it has ester functional group. Look at this carbon connected with the double bond to the oxygen and through another oxygen to the rest of the molecule. Here is the functional group of an ester, and here and here. So this is a clear-cut ester. And here is my inorganic base, very recognizable sodium hydroxide. So when sodium hydroxide meets ester, these 2 compounds react in the following manner. This connection over here breaks, and hydroxide groups from the sodium hydroxide will attach themselves in place of this esterification group, while the leftover pieces of this compound will be connected to sodium, and that will be soap. The other product of this reaction is alcohol. This alcohol over here has a special name. It's called glycerol. just another look at the reaction of saponification. Here's my ester, here's my inorganic base. I know this is ester because I see ester functional group right here and here and here. And when ester meets sodium hydroxide, these connections get broken down. Hydroxyl group from sodium hydroxide comes around and forms glycerol as a result of the connection. And the sodium with the pieces and bits that were left over cut off from the molecule on the left now join sodium and form a soap. Okay, here are some practice questions that I want us to look at. What kind of questions you might be asked? Which equation represents fermentation? Well, if you remember fermentation well, it's a glucose that is turned into the ethanol and carbon dioxide. The answer number 3 is definitely the good one. Which organic prefix is matched with the number of carbon atoms that it represents? Well, you should be using your reference tables because there is a specific table of organic prefixes where you can look up the answer. Hept means 7. Okay, in terms, which terms represent two types of organic reactions? Well, let's eliminate not organic reactions. Well, sublimation and deposition. They are not even chemical reactions. Not only not organic, but they are not chemical reactions. It's a change of physical state. Sublimation is from solid to gas, and deposition from gas to solid by passing liquid. So sublimation and fermentation, no. Saponification and deposition, no. Saponification and fermentation, that's the answer. Both of them are the titles of two honorable organic reactions, production of the soap and fermentation, production of the alcohol and carbon dioxide. Which type of reaction produces soap? Saponification, of course. And which equation represents an addition reaction? Well, we should remember that addition is happening to unsaturated hydrocarbons. So this reaction over here that has two reactants and one product, chlorine became part of the newly formed molecule, is the reaction of addition. Reaction number 1 is actually a reaction of substitution. Let's see this question over here. Explain in terms of chemical bonds why the hydrocarbon is unsaturated. Well, the only hydrocarbon that I see here is this one over here, and it is unsaturated because it has a double bond. Identify the class of organic compounds to which the product belongs. Here's byproduct, and it is carbon, hydrogen, and a halogen attached to it. So this entire compound belongs to the group of halides. Write the molecular formula of Lianellic acid. Well, molecular formula represents all the elements in the molecule. So I will go around and count all the carbons in the molecule, and I will count all the hydrogens in this molecule, and all the oxygens that are there. And here comes my formula. Identify the type of chemical bond between the oxygen atom and the hydrogen atom in the molecule. So we're talking about this bond. Well, one thing that I know that oxygen and hydrogens, they are both nonmetals, so it's a covalent bond, and also oxygen is very electronegative compared to hydrogen, so I can call this bond polar covalent. And the last question, circle the organic acid functional group. If any in doubt, check table R to see how organic acid functional group looks like, but here it is.